Understanding circular motion is one of the most important topics in physics. It helps physicists in understanding how the Earth and its satellites rotate and the movement of electrons in the atom, for instance. As a child, you must have wondered why one is pushed to the left when turning right on a roundabout. In circular motion, there are two types of velocity to consider: angular velocity and linear velocity. Starting with angular velocity, conventionally, I like to think of angular velocity as what angle the object has been moved to or turned through in a given time. Theta, measured in radians, is simply the arc length divided by the radius of the arc. In a circle, the arc length will be 2 pi r as the circumference, and the arc radius will be r. Therefore, in a circle, there are 2 pi radians, or 360 degrees. Equating these, 1 pi radian is equal to 180 degrees. The angular velocity is simply the angle turned through in a given time. Omega equals theta over t. Another way of expressing omega is by 2 pi into f, as f being the angular frequency. There are 2 pi radians in a circle, and therefore having the frequency times 2 pi in one revolution would give you the angular speed. You must have already met the equation f equals 1 over t, and matching this you get omega equals 2 pi over t. Moving on to linear velocity, which is also known as tangential velocity measured in meters per second, because it is the speed at which the object would travel at if it were to immediately be let off its original circular path, and it occurs at 90 degrees to its radius of the path. The derivation of this is simply using theta equals the arc length over the radius, and using the fact that omega is equal to the change in the angle over a given time. Applying these, we get tangential velocity is equal to the radius into the angular speed. As the angular speed is usually constant, we can say that the velocity is proportional to the radius of the object, of the orbit. Moving on to centripetal acceleration, which is always directed towards the center of the circle, we can see here the derivation is as follows. We know that acceleration is simply the change of velocity in a given time, and we know that in the circular motion here, the change of velocity is simply the linear velocity, i.e. the tangential velocity, times the angle between which the object has been turned through over the given time period, i.e. t0 to t1. We know that delta theta over delta t is equal to omega, the angular velocity, and therefore acceleration is equal to the tangential velocity times the angular velocity, and using the previously known equation where omega is equal to v over r, we work out that acceleration is equal to v squared over r.